key distribution was a huge problem even for governments with a lot of money and resources. Corporations such as banks would send special couriers with locked suitcases containing keys across the world, a problem which was thought to be unsolvable. Let's go back to our Alice and Bob example. Suppose Alice is in the UK and Bob is in the US. In order to communicate securely, they have to exchange the password, which in this case is trusty8844. Here's one way to tackle the problem using multiple locks. Suppose Alice locked her message with her own lock LA, and sends it to Bob. Bob can't unlock the lock as he doesn't have the key, but then adds another lock to the message lock LB and sends it back to Alice. Alice then unlocks her lock LA and sends a message back to Bob. Bob only has his lock left, LB, to which he has the key. He unlocks it to finally decrypt Alice's message. So we're done with the key distribution problem, no magic involved. Unfortunately, no. It was found that for simple encryption this works, like with the Caesar cipher. Take letter G, Alice moves that back to D, then Bob turns the letter from D to A, Alice then reverts it to a D, and finally Bob completes the decryption from D back to G. But for strong encryption, like AES, this technique doesn't work. It's like socks. If you put sock A on, then sock B over sock A, in doing so, sock B has to be removed first. Last on, first off kind of deal. In order to exchange these keys, we'll need to institute what I call a little modern magic. Let's take a step back and describe the two-way function. Something that can be done, can be undone. Take a doubling function. 2 to 4 can easily be converted back from 4 to 2. Or take this exponential function, 7 raised to the power of x. If x equals 2, we get 49. To undo this, we can use the natural log function, like so. But there are one-way functions, functions that can be done but not undone directly. A common example of this is the modulo function. Let's take the example of modular arithmetic with the following example. Exploring x as 1 through 5, 3 to the power of x would be 3, 9, 27, 81, and 243. But 3 to the power of x mod 7 would be 3, 2, 6, 4, and 5. For those that don't know how modular arithmetic works, think of an analog clock. If we start the clock at 0 or 12 o'clock and input or add a 3 to it, what does that clock say? 3. Starting again, if we input 9, what's the value? 9. Starting again, if we input the value 14, what's the value, or what does the clock say? 2 o'clock. Let's do this again, but imagine the clock doesn't go to 12, but goes to 7. Plug in 3, you get 3. Plug in 9, you go past the 7, through 1, and land on 2. This is also what's called remainder arithmetic. 9 goes into 7 with a remainder of 2. If we examine the case where the function 3 to the power of x mod 7 equals 2, what's the value of x? Well, x equals 2 for the example here. But as you should be able to infer, there are many values of x that end up with a remainder of 2, like 3 to the power of 8 mod 7. So let's see how modular arithmetic can help us with our key distribution problem. First, Alice and Bob choose a number which they'll keep secret. Alice chooses 3 and Bob chooses 6, n sub a and n sub b respectively. Then they'll use the public function 7 to the n mod 11, and in a secure environment plug in their secret number n, and the result is the public number p. For Alice, 7 raised to the power of 3 mod 11 equals 2, or p sub a, and for Bob, 7 raised to the power of 6 mod 11 equals 4, or P sub B. For the third step, they swap their public keys and utilize the function p to the n mod 11, which will give them their shared key. For raised to the power of 3 mod 11 equals 9 for Alice, and 2 raised to the power of 6 mod 11 is also equal to 9 for Bob. They were able to swap their keys publicly and didn't have to worry about someone snooping, because only their private keys could be used to expose this shared key value. And this key distribution method is called the Diffie-Hellman-Merkle key exchange.